Types of functions. This video will cover 3 types of functions: injective functions, surjective functions, and bijective functions. Injective functions. A function f from a to b is said to be injective or one-to-one if every output in b has a unique input in a. In a mapping diagram, no 2 points in a will have the same output in b, hence the phrase one-to-one. So we can see we have set A is 1, 3, 5, and 7, and then set B is 5, 7, 8, 9, and 11. And 1 maps to 5, 3 maps to 7, 5 maps to 9, and 7 maps to 11. So no 2 inputs in A have the same output in B. So each element is a one-to-one element. So 1 maps to 5, it only maps to 1 element. So it's a one-to-one function. Note, it is not necessary that every element in the codomain has a corresponding element in the domain. In the diagram on the right, 8 has no corresponding input. However, the mapping diagram still represents an injective function. So we can just see 8 here has no arrow going to it, and that's okay. It's still an injective function. The main thing is that the function is one-to-one. So every output in B has a unique input in A. Horizontal line test for injective functions. So the red curve is the function y is equal to x cubed, and we have a horizontal line, so a dotted line. The diagram on the right shows the graph of y is equal to x cubed. If y equals x cubed is an injective function, then any line drawn parallel to the x-axis, such as this dotted line, will intersect the curve at most once. The diagram shows that y equals x cubed is an injective function. So if we were to move this line up or down, so long as it's still parallel to the x-axis, no matter where we move it to, it will intersect the graph, so the red curve, once and only once. Surjective, many-to-one functions. A function f is surjective if every element of the codomain is the image of at least one element of the domain. A surjective function may also be described as a mapping of A onto B. No element of the codomain is left unused. So in the previous mapping diagram, we could see that 8 was left unused. It had no arrow going towards it. So that's why it was not a surjective function. But in this mapping diagram, we can see every element inside of set B has an arrow going towards it. So no element of the codomain is left unused. So we don't have any elements with no arrows going towards it. Hence, the range and the codomain are equal. For any function f, if the range and the codomain are equal, then the function is surjective. Notice in this mapping diagram that A maps to f and B also maps to f. So that's okay. We can have 2 arrows coming out of 2 different elements in A and mapping to 1 element in B. It's still a surjective function. The main point of a surjective function is that there's no leftover elements in set B. There's no outputs that don't have an arrow going towards it. Horizontal line test for surjective functions. Consider the function f of or maps to or. If f is surjective, so if the function f is surjective, then every horizontal line drawn must intersect the graph at least once. The function y is equal to x cubed, which is the same function from the previous example, where x is an element of the real number set, is surjective as every horizontal line intersects the graph at least once. So again, we have our red curve that represents the function y is equal to x cubed. And again, we have a horizontal line that's parallel with the x-axis. And if we were to move this line up or move it down, it will intersect the graph at least once. And finally, we have bijective functions. A function f is bijective if for every element y in B, there is exactly one element x in A such that f of x is equal to y. Therefore, a bijective function is both injective and surjective. That's why it's called bijective, because it's both. From the diagram, it can be seen that there is an exact one-to-one match between the elements in A and B. This function is bijective. So we can see we have 4 elements in A, 1, 2, 3, and 4. And we also have 4 elements in B, 1, 4, 9, and 16. So 1 maps to 1, 2 maps to 4, 3 maps to 9, 4 maps to 16. So every element in A maps to one and only one element in B. So therefore it's injective. And there's no leftover elements inside of set B. So the codomain and the range are the same. We've no elements that are missing an arrow. So therefore it's also surjective. And since it's injective and surjective, it must also be bijective. So this particular function must be y is equal to x squared, because 1 squared is 1, 2 squared is 4, 3 squared is 9, and 4 squared is 16. But this is only one part of that function. So that's how those numbers would make sense. But notice that there's no -4 in set A, for example. If -4 was in set A, -4 would also map to 16. So we would have 2 arrows going to 16. And if that was to happen, then we would not be able to call this an injective function. So therefore, it would also not be a bijective function. So this is only a certain range of the elements of what could have been in set A. So it's just a selection of the elements of the function y is equal to x squared. State whether the following maps A to B are functions, injective, surjective, or bijective, and give reasons for your answer. So we can see that each of the elements of A has only one arrow coming out of it and going to an element inside of set B. But notice that in set B, there is one element that doesn't have any arrow going towards it. So f is a function. There's only one arrow from each element in A. So all of the elements in set A have one arrow and only one arrow coming from it. F is injective. It's an injective function because each element in A maps to only one element in B. So each element in A maps to only one element in B. There's only one arrow coming out of each element in A. F is not surjective. It's not surjective because an element in B is not in the range of F. So we can see highlighted there, as I discussed a minute ago, there's an element in B that does not have an arrow going towards it. So therefore, it cannot be bijective, because in order for a function to be bijective, it has to be injective and surjective. And since it's not surjective, it can't be bijective either. So as it is not both injective and surjective. So F is not bijective as it is not both injective and surjective. B. Okay, so in set A, we have 1, 2, 3, 4, 5 elements, and each of them have an arrow leaving it. And in set B, we have 5 elements as well, and each of them have an arrow coming towards it. So there's no elements in set B that are missing an arrow. So G is a function because it only has one arrow from each element in set A. It is injective because each element in A maps to only one element in B. So it's a one-to-one function. So there isn't 2 arrows coming out of any of the elements in A. It is surjective because each element in B is the image of some element in A. So unlike the previous example, there's no elements inside of set B that are missing an arrow. So no elements in B without an arrow. So therefore it must be bijective, because it is both injective and surjective. Next we have C. So we have 5 elements in set A, and we have 5 elements in set B. But notice that one of the elements in set B has 2 arrows coming into it, and one of the elements has no arrows. So H is a function because there's only 1 arrow from each element in set A. H is not injective because there's more than 1 element in A maps to the same element in B. I've highlighted them in yellow. We can see there's 2 arrows going towards the same element in set B. So therefore it's not injective. So it's not a one-to-one function. It's also not surjective. And that's because all elements in B are not included in the mapping. We can see that there is an element highlighted in yellow that has no arrow going towards it. And therefore it's not bijective. So if it's not surjective and it's not injective, it's not bijective either. Because in order for a function to be bijective, it has to be injective and surjective.